Hello and welcome to Portland Community College's G147, Geology of the National Parks. This is taking place in winter of 2026. It is a 4-credit class with an online lecture, that is this part, the recorded video lectures, and an in-person lab portion which occurs at the Sylvania campus Wednesdays at 1 p.m. to 3:50 p.m. in room 317 in the Science and Technology building. Geology is its own science, and like all sciences, it has its own language, so you are basically going to be learning the language of geology. New words for minerals, rocks, landforms, different processes, and all sorts of things. A lot of these, I can only do so much as far as telling you what they are, what they mean, what they represent, but it is ultimately up to you to understand what they are, and you'll just have to memorize them, which is true with pretty much every science, and as it is with any language as well. So this course really is a introductory geology course with examples from the national parks, rather than it being strictly geology of every national park in order or some other way. There are 64 national parks. Unfortunately, we'll only be covering a fraction of those in this course, as again, this is a introduction to geology with examples from national parks type course. This course is not dictated by a textbook, and reading material will be assigned as needed from this open source education resource called An Introduction to Geology, which is provided by Salt Lake Community College. It's quite good for an open source education resource, as many of them are. And I mean, the cover photo they use for the textbook is Arches National Park in Utah. So it does contain examples from national parks as well as this course does. We will also have occasional readings from the National Parks Service website, where they have tons of resources on geology, as it is an important part of many national parks. Some basics first of all. We know the chemistry of the entire Earth, and by we I mean geologists. The geological scientific community knows the chemistry of the entire Earth. The entire Earth has a slightly different chemistry from the crust, the surface of the Earth where we live and what we can see for the most part. And this is called differentiation. The Earth is differentiated into different chemically distinct layers. Each different layer has a different chemistry, a unique chemistry, and a different density, different material properties. And it's the material properties and the chemistry together which defines these different layers of the Earth. Differentiation is this week's new featured word for you, so make sure you write that down and give it a good definition. It is the process of separation of different chemistries. In the Earth, differentiation produces the different layers of the interior. Going all the way back to the beginning, to the formation of the Earth, there is a lot of iron floating around in space, surrounding the sun as it was beginning to form, and this iron coalesced and formed the cores of most of the planets, in particular the rocky planets that form the interior of the solar system, that is Mercury, Venus, Earth, and Mars. They all have cores of iron metal. That is the center part of the planet, the core, which occupies, on the Earth, about half of the diameter or radius, but only about 15% of the volume of the Earth. The rest of the Earth is made of rock. So just to repeat, the core is made of liquid and solid metal. The inner core is solid, the outer core is liquid, and then above that is all rock. The mantle and crust are both composed of rock. So iron being the most common element in the Earth, making up about 1/3, 32% of the Earth's entire composition. The next most common elements are going to be oxygen and silicon. A lot of people are surprised to learn that oxygen is the second most abundant element on Earth. In the solid Earth, that is, we generally think of oxygen as a gas, but it is actually very present in the interior of the Earth because it is bound up with other elements, chiefly silicon, magnesium, and other lighter elements, but chiefly silicon and magnesium. The elements that oxygen and silicon bind with, we actually classify or differentiate the chemistry of rocks based on their silicon content. And when it combines with oxygen, it creates a mineral called silica, SiO2, or silicon dioxide. We classify rocks based on their content of silicon dioxide. There are four main classifications of rocks that we classify based on their silica content. We have ultramafic, which has very little silica, less than half of it, of the rock's composition is silica. They are enriched in magnesium, calcium, iron, and other heavier elements. When you move up to mafic rocks, you have about 50%, slightly less, slightly more silica. You still have a lot of aluminum, a lot of iron, a lot of magnesium, a lot of calcium. These are very present in mafic rocks. Then in intermediate composition, you are more than half silica. You still have about the same proportion of aluminum, but you have decreasing amounts of iron, magnesium, and calcium. By the time you get to felsic rocks, those are the highest proportion of silica. You still have about the same proportion of aluminum, but then you have next to no iron, next to no magnesium, next to no calcium, and increasing amounts of sodium and potassium, among with other alkali elements. The Earth's metallic core, as we already discussed, makes up about 15% of the volume of the Earth. The large rocky layer outside of the core, so between the surface and the core, is the mantle, which makes up about 84% of the volume of the Earth and approximately half of its diameter. This is made of ultramafic rock, such as a granite peridotite or a dunite. These green rocks are what makes up most of the mantle. The oceanic crust, which is the outermost layer, the crust, where we live and most of the things we can see are the crust, has two different types. We have oceanic crust and we have continental crusts. Oceanic crusts are underneath the oceans and continental crusts are on the continents where we live. The oceanic crust, for example, is made up of dark-colored mafic rock, chiefly rocks like basalt, which is what we have here in this picture here. The sea floor is made up mostly of basalt, except for areas where it's been buried by oceanic mud called ooze. But the underlying rock beneath the oceanic sediments is almost entirely basaltic rock. Where we live on the continents, the continental crust is composed of a wide variety of different types of rocks, but most of these, especially down deeper in the crust below the surface, are made of lighter colored, lower density rocks than the oceanic mafic rocks, and these are felsic in composition. That means they are rich in silicon dioxide, which is also the mineral quartz. Crustal rocks are differentiated into mafic and felsic. Mafic rocks are the ocean, and felsic rocks generally are the continents. So we've already discussed about separating out the Earth's layers based on their chemistries. We have that metallic core area. Then we have the rocky mantle and crust. And the crust itself has two different compositions. Oceanic crust, basalt. It's generally very thin, only 5 to 7 kilometers in most places. And then the continental crust is not only much thicker, but much less dense, being 10 to 70 kilometers in thickness in most places. We're going to take a bit of a leap and talk about some basic material properties, stress and strain. Stress is a force applied over a given area, and there's three different kinds. There's tension, compression, and shear. Tension is when something is being extended or pulled apart. Compression, things are being squeezed together. And then shearing, we have a rotational stress. So in this cube, it's being deformed or strained by opposing forces that are meeting each other at an angle rather than head-on like we have in compression. And that gives a rotational stress. This block is trying to rotate in a clockwise manner. And that's the way it's being strained. So in this rock, the strain is extensive, so it wants to break down the middle and break apart. The compression force on this cube, the strain, is for this block would collapse downwards and become smaller, and this one is being rotated. So it would also break apart in the middle, but so it could slide if it were to break. There's a few more important properties. Types of deformation, types of strain. We have elastic, plastic, and brittle. Elastic is most similar to a rubber band where you can stretch something and it will snap back into shape. Plastic deformation is when something can be bent, it can be deformed, but you can't really put it back to the way it was again. It's been altered from its original state by plastic deformation. And then brittle is easy, it's just when something breaks. Like this rock has broken from brittle forces, which makes it into these individual pieces, separated by fractures. This is called the yield point, where something goes from elastic or plastic deformation to brittle failure. That's called the yield point. So something can be strained where you have elastic deformation, then it hits a point where it cannot deform anymore, and it breaks. It returns to its original shape, and it breaks. So you have a big fracture. So the shape, or rather your object, is in its original shape, but now it has a fracture in it, separating it into multiple pieces. With plastic deformation, you have the same sort of thing, the same yield point, but instead of breaking, your object deforms permanently into a different shape, just like that paperclip does. A classic material that has both brittle failure and plastic deformation, or elastic deformation rather, is a piece of dried spaghetti. You can bend it a long ways. Eventually it will break, and that's your yield point. But before it breaks, and actually after it breaks, it will return to its original shape, which is a straight piece of dried spaghetti. If you pass the yield point, then you have a couple of pieces of straight dried spaghetti that have returned to their original form, albeit fractured. Earth's layers, as we already discussed, are differentiated on both chemical and mechanical or physical properties. So in addition to the crust, mantle, core properties of their different chemistries, we also have mechanical or physical properties separating out the planet into different layers. Up on top we have the lithosphere, which is generally from 5 or 10 kilometers thick to 200 kilometers thick. It incorporates the uppermost part of the Earth, so you have crust and mantle rocks, which are both felsic, mafic, or ultramafic, topped by a thin layer of continental crust, or oceanic crust. Below that, we have a very soft layer called the asthenosphere. Now, it's not liquid, but it's more like the consistency of a putty, like silly putty, for example. It's very soft. It's what we call a plastic solid that deforms plastically rather than brittly. The lithosphere deforms brittly. It generally tends to break rather than bend. Below that, we have the lower part of the mantle called the mesosphere. This is also a plastic solid. It is slightly less plastic than the asthenosphere is, but it is all mantle rock. It's all ultramafic material. Below that, we have the core. The core is actually broken out into two parts, a solid inner core, it's just a ball of metal, a solid ball of metal. Then after that, we have a fairly thick layer of outer core, which is liquid metal. So to recap, going from the inside to the outside, solid inner core, liquid outer core, solid but plastic mesosphere, very plastic asthenosphere, but it's not liquid, and then we have a solid lithosphere on the outside of the planet. And here's both of those different differentiations shown side by side. So to recap, the interior of the Earth is very, very hot. It has both liquid and plastic solid layers. These cool by convection. We'll touch on this in the next lecture. But the lithosphere is basically floating on the asthenosphere. Both of these layers, again, are solid, but one is brittle and doesn't flow, while the asthenosphere, which is below the lithosphere, does flow, and it deforms plastically. There's a concept called isostasy, which governs sort of the shape and how the lithosphere flexes rather than breaks, which it does do over broader regional scales, but we'll touch on that in the next lecture as well. The most important geological theory to sort of come out in the last 100 years or so is that of plate tectonics. The basic idea of plate tectonics is that the interior of the Earth cools by a mechanism called convection, where hot material rises and cooler material sinks. The brittle lithosphere has broken up into a bunch of different pieces, which we call plates. And these tectonic plates, or continental lithosphere, are too buoyant, really, to sink into the mantle. However, oceanic crust, oceanic continental plates, are that mafic rock. They are cold, they are very dense, and it sinks back into the Earth in places called subduction zones, where it is eventually remelted and recycled into the mantle. There are 3 different kinds of plate tectonic boundaries, but we will talk about these in greater detail in the next lecture. Plate tectonics have a couple of important features. Most volcanoes and most earthquakes occur at or along plate boundaries. This is a map of the world's volcanoes shown here. We have the Pacific Ocean, which has a huge concentration of volcanoes all around its perimeter. Some people call this the Ring of Fire, but this is not one structure, it's not one system, so it's not one single Ring of Fire. That's definitely a misconception that most people have about how the quote-unquote Ring of Fire works. But below that, we have this map of the Earth's earthquakes, which are also concentrated along plate boundaries. We have shallow earthquakes at one type of boundary called divergent boundaries. These are in the center of most of the world's oceans. And then where we have continental plate boundaries, we have generally deeper earthquakes, which occur along subduction zones where oceanic crust is sinking down into the interior of the Earth. These 2 videos that are linked show you something called a Wilson cycle, which shows how oceans open up and then close up over geologic time. This is also how continents occasionally bunch up together into supercontinents like Pangaea. And then over time, you can see what the Earth's continents have done over the last roughly 500 million years in this second video that's been linked. And then these are some image sources for some of the images used in this slideshow presentation. This has been topic 1 of lecture 1 for week 1 of Geology of the National Parks.